Everybody, I think we are hitting quorum. The room is filling up, so I think we should get started with the next session because it is full as well. Okay, yeah, thanks for coming back, and yeah, please, I think everything is set up, so please take it away when you're ready.
Working? Okay. Great. Okay. Okay, well, good afternoon, everybody. My name is Rupanshu. I'm a CS PhD student at Stanford. This is joint work with Qiantan, Yihong, Zhang, and Alex Aiken. So we call this project Rewrite System Showdown because we're trying to do the first rigorous comparison of equality saturation with another program optimization technique. And this is in reference to a PLDI paper from 1995, which does the same thing for software pipelining, which I recommend if you're interested. Okay, so EqSat, of course, extremely popular, egg and egglog, and now many other implementations for different languages like Python, OCaml, Common Lisp, Haskell, what have you. And the number of projects that are about EqSat or use EqSat are simply too large to fit on a single slide anymore. And just anecdotally, it is very common to see at top PL venues a couple of papers that are about EqSat or trying to invent a variant of EqSat. I think at this PLDI there are 5 by my count. My point is that our community really cares about this technique. However, EqSat has a number of famous limitations. So it has trouble with AC rules, which can blow up the eGraph. Things like variable bindings are hard to represent. Control flow is hard to represent. Optimal extraction can be really slow. And not to mention things like optimistic analyses, context-aware reasoning, or parallelizing EqSat. However, very interestingly, instead of moving us away from EqSat, these limitations have had the exactly opposite effect. These limitations have engendered a flurry of papers that explore variants of eGraphs in an attempt to fix some of these problems. And this is an exciting and rapidly progressing area. And just today morning, we saw several papers trying to add AC theories to eGraph. And so this work is by no means done. So there's more work to do for making EqSat more scalable, better suited to certain class of programs, etc. However, let us take a step back. Why are we doing this in the first place? Why do we use EqSat at all? I would claim that people use EqSat not because it is fundamentally better than other program optimization techniques, but because of more practical reasons, like frameworks like egg and egglog are really easy to use, and EqSat is now extremely popular. But nobody seems to have done an extensive comparison to actually determine if EqSat is the right tool for their problem. Is there an alternative? EqSat solves a certain kind of problem. Are there other methods to solve the same problem? Well, EqSat is not the only one. Perhaps the main contender is stochastic search. So I'll give you a 101 on stochastic search. Instead of maintaining an eGraph of equalities, we're going to maintain a single concrete term at a time. We're going to have the same rewrites as equality saturation, but we're going to apply these rewrites probabilistically and in a cost-guided manner. So you might start with some term like this, and with some probability, you might transition to some new terms like this, and you can just keep doing this. This is not a very intelligent approach, but you can do this extremely quickly, and you can scale this. This process is embarrassingly parallel. So if you have 128 CPU cores, you can scale this to 108 CPU threads. So this is a very powerful technique, and it solves the same kind of problem that EqSat solves. Furthermore, egg's interface is very general, And the same interface can be implemented by stochastic search. So E-class analyses, for example, can be implemented for stochastic search just by porting the analyses to work on like concrete terms instead of E-classes. So what we do in this project is we write an implementation of stochastic search that follows the same interface as EGG. And then we do an extensive comparison over a number of benchmarks to see which one wins. Okay, so now I want to discuss our 5 benchmarks. So our goal is to cover a variety of use cases. So we're going to see some benchmarks that are small, self-contained applications, but then some like larger, substantial ones taken from prior work. And so when we run EqSat and stochastic search, we're going to give them both the same amount of wall clock time, but we're going to run stochastic search with 128 threads. But EqSat is run with only a single thread. So this gives stochastic search more CPU time, but not more wall clock time. And we would argue this is a fair comparison because the algorithm is just embarrassingly parallel. Okay, so let's see our first benchmark, which is a small self-contained application. This is the classic matrix chain multiplication benchmark. So say you have 3 matrices of different sizes, but which are compatible. Say you want to compute the product, ABC, of the 3 matrices. There are 2 ways of associating this product. Which association minimizes the number of scalar multiplications? So this is what we want to do. Like given some large product of matrices, we want to find how to carry out this product so that we minimize the number of scalar multiplications. So we're going to solve this problem using EqSat and stochastic search, and we will compare the solution quality obtained by both approaches. Another good thing about this benchmark is that there's a fast polynomial time algorithm to solve it. So we can just find the optimal solution, and then we can see how close to optimal both techniques can get. Here are the results. So on the x-axis, I gave the number of matrices in the test case. This is randomly generated. And on the y-axis, I gave the ratio of optimal cost to cost found by either technique. So you want to be as close as possible to the y=1 line here. So we see that until about 300 matrices or so, both techniques are extremely close to optimal. But as we go above 300 matrices, EqSat just falls off rapidly. And this makes sense because this search space is just too large, and EqSat doesn't have any cost guidance. So it just cannot figure out the right association in such an enormous search space. Stochastic search does well and stays almost close to optimal throughout all the test cases, because it is cost guided. Like every time stochastic search makes an association that drops the number of scalar multiplications, the search is reinforced in that direction. And so it can just hill descend to the optimal solution. I also want to point out one more interesting thing, which is that below 300 matrices, so in the regime where both techniques are about the same, EqSat usually finds the optimal, where stochastic will sometimes find something that is only close to optimal, but not exactly optimal. And this difference was about 0.3% in our experiment. So there is a bit of a difference in how they perform. Okay. Next benchmark. This is another self-contained application. We're going to do trig simplification from like your high school math class. So we collected 35 trig problems, such as proving this trig identity. The rewrite rules for this are going to be standard algebraic rules plus some like standard trig identities like the ones you see on the slide. And we're going to optimize AST size, so like a very simple cost function. So for each of the 35 problems, we have an intended solution, which we literally took from the textbook these problems are from. And so I'm going to consider a problem solved if a technique finds a solution that is no worse than the intended solution in terms of AST size. Here are the results. So now I give stochastic search cost on the x-axis and EqSat cost on the y-axis. So points on the y=x line are problems on which both techniques found something of equal cost. Points below the line indicate problems where EqSat was better, and points above the line are problems on which stochastic was better. So overall, 23 out of 35 problems were solved by both techniques. Then there were 3 problems that EqSat solved and stochastic did not solve, and 3 problems that stochastic solved and EqSat did not solve, and 6 that neither solved. Okay. So I guess overall, neither technique comes out to be Pareto optimal over the other. There's a core set of problems that both can solve, and then a few on which either one manages to eke out an edge. The third benchmark is, again, like a high school math thing, indefinite integration. So we're going to do 10 problems of indefinite integration, so like doing the integral of x cos x. So the results here are very similar. We have 6 problems that both solve, 1 that EqSat solves and Stochastic doesn't, 2 that Stochastic solves but EqSat doesn't, and then 1 that neither can solve. Okay, so again, like neither seems to be Pareto optimal over the other. There's like a core set that both can solve and then some outliers. I want to highlight one issue that arose in this benchmark. So a very productive rewrite rule for doing indefinite integration is the linearity of integration. The problem is that under the standard like AST size thing, from the eggs math example, the right-hand side is going to have higher cost than the left-hand side. And this is very problematic for stochastic search. If you have a cost increasing rewrite, stochastic search is not going to apply it very frequently. So this is going to cause problems for stochastic search. To fix this, what we do is we modify the stochastic cost function to square the subterm. And if you like stare at this for like 5 seconds, you can convince yourself that this changes the linearity of integration to be a cost decreasing rewrite. So the point is just that sometimes you might need to tinker with the cost function a bit to enhance the performance of stochastic search on some benchmarks. EqSat, of course, does not care because it's not cost guided at all. Okay. So now we move to our fourth benchmark, which is a more substantial one. So this is a tool called Zelinsky, published in PLDI 2020. Zelinsky takes unstructured CAD programs, like the one you have on the screen, which represents 5 cubes placed in a straight line. And Zelinsky is going to decompile them into a more structured CAD representation that uses higher order combinators like folds and maps and so on. So we re-implement Zelinsky with stochastic search. We keep all the same rewrite rules and the E-class analyses. And actually, the total effort in porting this to stochastic search was only mild, because as I said previously, stochastic search can implement basically the same interface as EQ. Okay. So here are the results. So again, I'm going to plot cost of stochastic on the x-axis and the cost of EqSat on the y-axis. And so now we have 2,000 problems. And let's see, on about 600, stochastic and EqSat are tied. So they found a solution of equal cost. EqSat finds a solution of lower cost on about 800 problems, and stochastic finds a lower cost solution on about 700 or 730 problems. So EqSat seems to have a slight edge in this benchmark. And that this is not surprising, actually. Zelinsky's rewrite system happens to be ill-suited for stochastic search, and I want to explain why this is the case. So what you typically find in Zelinsky is you have a program like this, and it gets folded into a higher level representation that uses functional combinators. However, usually programs are not in this nice form. They're in some like other form. And before you can do the nice rewrite that folds it into a higher level program, you need to get all the subterms into the right form before the final rewrite can fire. And so this causes problems because you don't get a lot of guidance from the cost function before the final rewrite has been applied. So to illustrate the problem more, I'm going to consider an abstract rewrite system to model this problem. So say I only have 3 rewrites. A goes to B, B goes to A, and F of 3 B's goes to G of 3 B's. You can represent the system with these 2 cubes. So each vertex in the cube is a concrete term induced by this rewrite system. And then there is one step you can take from one cube to the other. Okay? Otherwise, you can always move from like 2 vertices of the same cube. In Zelinsky, what we're trying to do is we're starting from the F3A's vertex, and we're trying to go to the G of AAA vertex. And this is really so imagine that the cost function that is guiding stochastic is like 1 everywhere, but 0 only for the end vertex. So there's like no guidance at all. And so basically what's going to happen with stochastic search is it's just going to like wander around in this like left cube until it just so happens to get to the right vertex and happens to apply the one rule that gets you to the right-hand side cube, and then it will wander around in the right-hand side cube until it gets to the end vertex. So it just doesn't get a lot of guidance at all. And if you have a problem for which you do not have a good cost function that can provide guidance to the search at every step, stochastic is going to struggle. Whereas EqSat can do this problem in like 2 iterations, actually. Okay. So our last benchmark is from a CC paper of 2022, and this paper uses equality saturation to prove inequalities inside the halide compiler. Okay, and so now we have about 6,000 problems, such as proving that max of I, 2 is less than max of I plus 3, 3. Here are the results. So we again, it's the same kind of thing. We have a core set of problems that both techniques solved, and then a few that EqSat solved and stochastic didn't, and some that stochastic solved, EqSat didn't, and then a large set actually that neither could solve. And this is not surprising because it just so happens that the rewrite set in this paper is quite weak and therefore insufficient to prove every problem. Okay, so those were our 5 benchmarks. Let's take a step back and see what we learned. First, as I've been saying, neither technique is Pareto optimal over the other. Some hyperparameter tuning is required for both. For EqSat, you may need to do some rule scheduling. For stochastic, you might need to change the cost function a little bit, or you might need to tune your restart schedule. I didn't discuss restart schedules in this talk, but you can see the preprint for more details. Stochastic is also more scalable. It really benefits from having 128 threads. Like the results are much worse if I run stochastic with like 10 threads. And the number of candidate programs that stochastic considers really does scale linearly with the number of threads. And then finally, another useful property is that stochastic uses constant working memory. And this is in sharp contrast to EqSat, where the working memory goes up monotonically with time. So in this project, we looked at 2 techniques that solve the same problem. But to be more... 5 minutes. Okay. But like, which problem is it? So we call this equational program optimization. So traditionally, people only use EqSat to attack this problem. But by decoupling the problem definition from its solution strategy, we can see that there are many more ways of solving these problems. In fact, there's a whole zoo of equational program optimization techniques. There's EqSat and stochastic, of course, but you can do beam search, you can do A star, you can do greedy, or you can invent your own thing. Why are we limiting ourselves to only one member of the zoo? As a concrete example, consider pulsing, a technique that marries EqSat and greedy search. So pulsing is a common trick in the literature in which the idea is that you do EqSat for some amount of time, extract the best term in the eGraph, use that to seed a new eGraph, and you keep doing this until your budget is exhausted. And if you implement pulsing on the matrix chain multiplication benchmark, it really, really helps EqSat scalability, as you can see. And EqSat and stochastic search need not be enemies. They can be friends. They're part of the same zoo. So one direction I'm excited about here is, can we find a new technique that is Pareto optimal over the other by marrying their strengths together in the right way? So one example could be to do a little bit of stochastic search, find a diverse set of programs, and then do equality saturation on those programs so that equality saturation does not get stuck in local minima. And just as a parting thought, there is more to say about stochastic search. On the trig benchmark, if you implement a new secret optimization that I cannot tell you about right now, stochastic search actually beats EqSat. And if you want more details, you should talk to my co-author Qiantan, who's in the front row later. Thank you for listening. Thanks for your attention. I'll be happy to take any questions.
Thank you so much. We have time for a couple questions.
So you made a big deal in the talk, maybe an implication that the cost guidance is one of the main reasons stochastic search can, in many instances, outperform eGraphs. But then you pointed out that and that this also allows it to scale. What strikes me is that the clever part of EGRAPHS', the term canonicalization, doesn't really have anything to do with the cost guidance. You sort of pointed that out when you did the pulsing, which is a kind of cost guidance. Do you want to say a little bit more? Is there some utility to the canonicalization aspect that you could add to Stochastic?
That's a great question. I mean, that is kind of the thing I'm hinting at. There might be techniques that are hybrids of the two. So maybe you do a little bit, you keep around an eGraph of the best things you've seen, but then you do stochastic search to find more things, more terms. So they're definitely, I don't know exactly what it would look like. I do think the canonicalization is helpful, but I don't have any results to ablate out the effect of the canonicalization from the other things. But I am definitely excited about doing hybrid techniques that get the best of both worlds.
So when you pulled up the indefinite integration thing and you talked about that little trick to massage stochastic search into using the linearity rule. So how much of this is dependent on the rule set? So maybe certain rule sets are better for EqSat, certain rule sets are better for stochastic search, and you just need to massage the rule set into specific ways to make them work.
Yeah. So I don't have a good characterization for you for when a rule set is better for EqSat and stochastic search. That is an interesting question. In all the experiments we did, we used all the same rewrite sets for both. So this is something we were careful about. Does that answer your question?
No, so this is just an open question. Maybe someone should.
Someone should.
Okay, I think we should leave it there. Let's thank the speaker one more time.